morning. In today's session, I will be discussing about the simple stresses and strains, some numerical examples on this topic. You know what is simple stress? Simple stress and simple strain. That means when a member is subjected to some axial force, direct force, then it will be subjected to some strain. When a member is subjected to axial pull or push, it will be subjected to some strain which is equal to stress by Young's modulus. By Hooke's law, you know the relation E is equal to stress by strain. So the strain to which the member is subjected is stress by Young's modulus. Strain means extension or contraction divided by the length, actual length of the member. That is the strain. Change in length by original length. That is the strain of the member. And stress means the intensity of load acting over unit area. The load acting over unit area. So it will have the units of Newton per mm square or kilonewton per mm square, kilonewton per centimeter square or meter square, whatever. Okay. So it will have the units of Newton per mm square. So the Young's modulus of the material, it is a material property actually. So for a material, the Young's modulus remains same. For the same material, Young's modulus remains same. Okay. So for different materials, Young's modulus may vary from material to material. Say for steel, it is around 2 into 10 power 5 megapascals or Newton per mm square. Okay. Similarly for other materials such as aluminum, brass, the Young's modulus values will be different. Okay. So here, to find the extension of any member, longitudinal member, subjected to axial force P, we use this expression E equal to stress by strain. Okay. So here stress is P by A and strain is delta L by L. So from this, the extension or contraction delta L is equal to PL by A. Okay. The extension of the member is given by this expression PL by A. This is for a member of uniform cross section. This is for a member of uniform cross section. That means cross sectional area is same throughout from one end to the other end. For such a member, we can find the extension or contraction by using this expression. Okay. So this is the basic equation. These are the basic equations for stress, strain and Young's modulus, okay, and extension. Using this, we will solve some simple examples, numerical examples. First example is the case of a bar consisting of different diameters, 3 different portions. Here we have with 3 different diameters. The bar is same, material is same for the bar, but it has not, it has different diameters. Okay. So the end parts are 25 mm in diameter and middle portion is 20 mm in diameter. The lengths are also different. For end portions, the lengths are 150 mm each, and for middle portion, the length is 250 millimeters. Okay. So the member is subjected to axial pull P, which is of magnitude 40 kilonewtons. The axial pull is 40 kilonewtons. And the total extension of the bar is given here. Total extension of the bar is given as 0.28 millimeters. And you are asked to find the Young's modulus of the material. You are asked to find the Young's modulus of the material. So, we have seen the expression for elongation for a uniform member with uniform section. Here the member is not of uniform section. It consists of different diameters in 3 different portions. So, how to solve this example is by considering the free body diagrams of the portions A, B, B, C and C, D separately. All these 3 members are subjected to tension. So, considering portion AB, it is subjected to a force P at the left end, axial pull. So, for equilibrium, there must be a force P balancing the applied force. So, this force must be tensile. That means acting away from body. So, for equilibrium of portion AB, we have axial pull here, P of magnitude 40. Okay. That means the member portion AB is subjected to axial pull. Isn't it? Similarly, portion BC, if you consider, so it will have a force P here to balance this, acting in opposite direction. That means towards left. So when you cut this section here, you will have 2 forces acting, 2 equal and opposite forces acting at B. Similarly, if you cut this at section C, you will have 2 equal and opposite forces acting at C. Okay. That means if you consider portion CD, it is also subjected to an axial force of P at C. Okay, to balance the applied force P at D. Okay. So, all these 3 portions are subjected to tensile stresses. Tensile stresses. That means all these 3 portions are, they undergo extension. All these 3 portions undergo tensile strain. That means there will be some increase in length of these 3 portions. Okay. And what is given is total extension is given of the bar. Let it be delta. Total extension of the bar is given as 0.28 millimeters, delta. So, how will you get the total extension here? The extension of portion AB, extension of portion BC and extension of portion CD. Okay. That means delta is equal to, total elongation is equal to the sum of the elongations of portions AB, BC and CD. So, let delta 1, delta 2 and delta 3 be the elongations of portions AB, BC and CD. Okay. So, the total extension is given as delta 1 plus delta 2 plus delta 3. So, what is delta 1 now? You consider AB as a member. The portion AB as a member which is of uniform section D1 of diameter 25 mm, okay, subjected to axial pull of 40 kilonewtons. And we have seen already the expression for a member of uniform section. The elongation is given as PL by AE. So here for member AB, we take it as P1 L1 by A1 E. The material being same, E will be same for all the three portions. Okay. If materials are different, then E also will be different. Then we will take E1, E2 and E3 for three different portions. Okay. In this case, the material is same, so E is same for all the three portions. Isn't it? So here P1 means 40 kilonewtons. So we substitute load in newtons, multiply with 1000, and L1, the length of member AB, which is 150 mm. The length of member AB is 150 mm. And A, what is the area of cross section? Pi by 4 into diameter 25 mm into E. We don't know what is E. We have to find the Young's modulus of the material. So this is delta 1. Similarly, we will get delta 2 as P2 L2 by A2E. So which is again P is same 40 kilonewtons and length is 250 for middle portion and diameter is 20 and Young's modulus is E. Okay. And delta 3 is P3L3 by A3E. And if you observe here, the length and diameter are same for portion A and portion C. So delta 1 and delta 3 are equal. The load being same, length and area also being same, the delta 1 and delta 3 are equal. Okay. That means what is delta 1? So if you add these two now, you will get total elongation which is given as 0.28. Okay. So here so it comes out, so we'll calculate this. So here 25 square here, so 4 into 4 into, you consider this as 40,000, 4 into 10,000 actually, divided by 25 square means 4 into 4 again, okay, into 150 by pi E. Okay. Similarly here 4 into 4 and 10,000 by 20 square. That means 5 into 5 we will have into 250 by pi E. And this is same as delta 1. So what is this value? 16 into 16 into 150. 16 into 16 into 150 divided by pi E. That is 256 into 150 by pi E plus delta 2 is 20 into 20. That is 400 into 250 by pi E plus delta 3 is equal to delta 1 again. So this is multiplied with 2. Okay. Now from this we will get Young's modulus. Okay. And what should it be? The Young's modulus is obtained as 2.0099 or 2.01, you can say, Newton per mm square. 2.01 Newton per mm square. 2.00090 Newton per mm square. 2.01 into 10 power 5 Newton per mm square. This is the Young's modulus for the given material. Okay. So when the member is having non-uniform section, different diameter sections, then we will calculate the total elongation as the sum of the elongations of individual portions. This is the equation, governing equation. Okay. If it is contraction, then delta 1, delta 2, delta 3 are also the contractions, that is negative values. Contraction is decreasing length actually. Contraction means decrease in length. So it is negative. Let us consider another example. So here a bar is consisting of two different materials here. The total length of the bar is 1.4 meters, 1400 mm, 600 plus 800. And the tensile force acting is same on both the members, both the portions. So we can consider this as A, B and BC, two different portions and two different materials. So it is not circular, actually it is of rectangular section. For portion AB, the width is 40 mm and let T be the thickness, which is 20 mm, which is given as 20 mm. And for portion BC, the width is 30 and thickness is 20. Thickness is same. So the cross section is rectangular here. Okay. And for material 1, the Young's modulus is given as 2 into 10 power 5 Newton per mm square. And for material 2, the Young's modulus is given as 1 into 10 power 5 Newton per mm square. And axial load is 30 kilonewtons acting at both ends. So if you consider the free body diagrams of portions AB and BC, both of them are subjected to same pull, 30 kilonewtons. So length of AB is 600 and length of BC is 800 and pull is same, 30 kilonewtons. Pull acting is same, axial pull. Okay. So how to find? What you need to find? The total extension of the member. The total extension of the member. Okay. So already we have seen what is the total extension for a bar with two different Young's moduli, two different materials, two different portions with different diameters. The total elongation is sum of the elongations of individual portions. Delta 1 plus delta 2. Delta 1 plus delta 2. Delta 1 plus delta 2. Okay. So what is delta 1? What is delta 1? It is P1 L1 by A1 E. E1 actually, because Young's modulus is also different here. P1 L1 by A1 E1. Okay. So A1 means area of portion 1, which is 40 into 20, 800 mm square, and A2 is 30 into 20, 600 mm square, and L1 L2 are given as 600 and 800 mm. Okay. Young's moduli are also given, E1 E2. Okay. So delta 1 is equal to P1 means 30, convert it into newtons, into L1 600 by A1 800 into E1 2 into 10 power 5. E1 is 2 into 10 power 5. E2 is 1 into 10 power 5. Okay. Plus delta equal to delta 1 plus delta 2. What is delta 2? 30 into 1000. 30,000 newtons. And length 800 divided by area 600 into 1 into 10 power 5. So the units will be now millimeters, because load is in newtons, length is in millimeters, Young's modulus is in Newton per mm square. So the resulting units will be in millimeters. Okay. And how much you will get the resulting value? The resulting value is 0.51. Actually, it is given as 0.5125 millimeters. You will get the total elongation of the member is 0.5125 millimeters. Okay. So when material is different for different portions, then we will use this expression. Previously, in previous example, we have taken E same for all the members because the material is same, but here the material is different, so we use the corresponding Young's modulus value, E1, E2 and so on. Okay. The basic equation is set. Let us now consider the third example. Let us consider this. Here, a bar of length 1000 millimeters, a borehole is driven at one end. The borehole is of diameter, this is not 30, 10 mm. The borehole diameter is 10 mm. And diameter of the bore is 30 mm. That means this is the bar and borehole at one end to a length of 400 mm. To a length of 400 mm. The borehole is driven for a length of 400 mm from one end centrally. Okay. And this is of diameter 10 and this is of diameter 30. Bar is of diameter 30. Okay. And it is subjected to an axial pull of 30 kilonewtons. And total extension is given here, which is 0.222 millimeters. Okay. And what you have to find is Young's modulus. We have to find Young's modulus of the member. And how to proceed, how to solve this. Okay. Here also the cross section is not same throughout. It is not of uniform section. Okay. So for this case, we consider two portions A, B and BC. B is taken at the end of the borehole. Okay. That means from B to C, the cross section is this one. So it has a borehole of 10 mm. 30 mm bar with the 10 mm borehole. Okay. So B to C, the cross section is this, and from A to B, it has solid section, complete circle. Okay. So this is A2, this is A1. The area here is A1 and length is L1. What is L1? 1000 minus 400, that is 600 mm. This is L2 and A2. What is A2? This one. So A1 is pi by 4 into capital D square. Here A is pi by 4 into capital D square, A1. And A2 is, for this portion, pi by 4 into capital D square minus small d square. Capital D is outer diameter 30 mm, small d is borehole diameter 10 mm. Okay. So these are the areas for two different portions. Material is same here. So we have to find the Young's modulus of that material. Total extension is given as 0.222. So we find the elongations of portions AB and BC, delta 1 and delta 2. And the sum of these two is 0.22 delta. Okay. So delta equal to delta 1 plus delta 2, which is given as 0.222. And what is delta 1? P L1 by A1 E. E is same. P1, P2 are also same here. P2 L2 by A2E. So what is the load P on both the portions? The tensile force of 30 kilonewtons is acting. So P1 is 30 kilonewtons. So convert into newtons, and L1 is 600 by A1, that is pi by 4 into 30 square into E. This is delta 1 plus P2, 30 again into 1000, and length is 400, area is pi by 4 into capital D square minus small d square into E, Young's modulus. Okay. And on the left hand side, we have 0.222, the total elongation given. Okay. So from this, E comes out to be 200,736. Already we have seen here 200,736. This is the Young's modulus. And units newtons per mm square. Newtons per mm square. Okay. So these are different examples. Okay. On simple stresses. And let us see one more example. The example of tapering cross section, tapering bar. The cross section is uniformly varying. Okay. Cross section is uniformly varying. A rectangular cross section with thickness T and depth varying from B1 at left end to B2 at the right end. At the left end, the cross section is B1 into T. At the right end, the cross section is B2 into T. Okay. So how to solve this type of problem? A tapering bar of length L and the cross section varying uniformly from one end to the other end. Okay. Here the cross section is rectangular. Okay. Varying from B1T to B2T. From left end to the right end respectively. So here what we do, we consider small element of the bar of length dx, okay, of length dx at a distance x from the left support, left end. Consider an element of length dx and width being b. Let the width at distance x be b. So the bar is subjected to an axial pull of P. So each and every portion will be subjected to so that means if you consider a portion here, this will be subjected to an axial pull of P. Okay. That means this delta x here also is subjected to the same pull P. Okay. And we consider the elongation of this elementary strip. Okay. And we integrate that between the limits of x from 0 to L. That means from left end to the right end, from A to B. Okay. To get the total elongation. Okay. That means first we will find out the elongation of an elementary strip and we sum up the elongations of such elementary strips from left to right, and that summation is done by integration. Summation is nothing but integration. It's okay. Between the limits of x from 0 to L. So what is the width of this strip B? Or width or depth? We call it depth. What is the depth of the strip here at a distance x? So the width is varying from B1 to B2 at A, B1 at B, B2. This happens in a length of L. In a length of L, okay, the width changes from B1 to B2. So what will be the change per unit length? Change in width per unit length. So change in width is B1 minus B2. In a length L, change in width in a length L. So change in width per unit length is B1 minus B2 by L. B1 minus B2 by L. Okay. So what is the change in width in a length of x? Change in width in a length of x. This is per unit length. So change in width in a length x is b1 minus b2 by L into x. That means per unit length, this is the change in width. Okay, isn't it? So in a length x, the change in width is b1 minus b2 by L into x. Okay, this is change in width. So what will be the width b now? B is equal to b1 minus change in width. Okay, b1 minus b2 by L into x. Okay, in a length of L, the change in width is b1 minus b2. So what is the width at b2? Width at b2, width at b is b1 minus b2 by L into L. Okay, that means in a length of L, the change in width is b1 minus b2, isn't it? So you will have b1 minus of b1 minus b2. That means b1 minus b1 plus b2. So it is b2, is it? So this is the equation we use to find the width at any section. To find the width at any section, we use this expression. For any distance x, the width is given by this expression. Okay, and for convenience, we take this b1 minus b2 by L as k. Okay, so the width at any section now is b1 minus b2 by L into x. This is b1 minus of this. So for the sake of convenience, we replace this for some time by k, where k is equal to b1 minus b2 by L. K is equal to b1 minus b2 by L. Okay. So now come back to this. So what is the elongation of this now? For a length L dx, for a very small length dx, the width is considered uniform. Width is considered same. Okay, over a small length of dx, the width is considered same, and this element is taken as uniform cross section. The cross section of this elementary strip is considered to be constant. The width is considered to be constant for this elementary strip. So for a constant uniform diameter or uniform cross section, the elongation is given as, elongation of the elementary strip here is given as PL by AE. Okay, the elongation of bar with uniform section is PL by AE. Okay, so what is A here? Area of elementary strip at a distance x, B into T. B is the width multiplied by thickness. B is B1 minus Kx into T. Okay, so the elongation of the elementary strip or the extension of elementary strip, the extension of elementary strip is equal to P into L. Length of the elementary strip is dx by Ax into E. Okay, Ax means area at distance x, which is b into t. Okay, so this is uh, the elongation of the small element. Okay, elementary strip of length dx. Okay, so this is p dx by b1 minus kx into t into e. Okay, and how will you get the total elongation of the bar, tapering bar? Okay, how will you get the total elongation now? Total elongation delta is equal to integral of p dx, integral of this. Okay, b1 minus kx t, because this is the elongation of elementary strip. Okay, the width being uniformly varying, we can find the total elongation by integration. Total elongation by integration. Okay, అంటే b being a function of the distance x, b being a function of the distance x, we can find the total elongation by integration. Okay, integration of the elementary strip, integration of the extension of elementary strip gives the total elongation of the member, tapering member, when it has definite relation with x, when the width is having definite relation with x. Okay, being a function of x, we can use integration for finding out the total elongation. Okay, so what is the integral of this? The total elongation is obtained as integral of this between the limits 0 to L. The limits of x are 0 to L. So you take the constants from this out of integral. P, T and E are independent of x, so you can take that out. 0 to L, 1 by b minus kx dx. Okay, so delta is given as p by te, and integral of 1 by b minus kx, it is in the form of 1 by x dx, integral of 1 by x dx. In place of x we have b minus kx, isn't it? So we can do this by substitution. B minus kx equal to t. So what is dx? Equal to dt by k minus dt by k. From this we get dx equal to minus dt by k. That means 1 by t dt minus. And what is the integral of 1 by t dt? It is log t. So minus p t e. Okay, isn't it? Into log t. So what is t here? We are substituting t for b minus kx. So log b minus kx, and dx equal to dt by k, isn't it? So we can take k also here. Okay, so we have k here. What are the limits now? 0 to, for t the limits are different, but for x the limits are 0 to L. In place of k, you substitute again. What is k? B1 minus B2 by L. So PL by TE into B1 minus B2. K is replaced with B1 minus B2 by L. B1 minus B2 by L. So L is taken to the numerator. PL by TE B1 minus B2. And by substituting here, for log k, b minus actually b1 minus b2 by L. Okay. It is b1 minus kx. Sorry. b1 minus kx. So substituting L here, the upper limit, what will you get? b1 minus of b1 plus b2. That means you will get b2 minus, when you substitute 0 here, when you substitute 0, the lower limit, what will you have? b1 and it becomes 0. So b2 minus b1. You will have log b2 minus b1. Sorry, log b2 minus log b1. Log b2 minus log b1. Okay. Log b2 minus log b1. So what will be the final expression here? Taking this negative sign inverse, so it becomes log b1 minus log b2. Taking this positive, you will have log b1 minus log b2, which is log of b1 minus b1 by b2. So delta is equal to PL by TE b1 minus b2 into log b1 by b2. This is the final expression for the elongation of tapering bar with rectangular cross section. The width varying from b1 to b2 in a length of L. Okay. So the final expression for the elongation is this one. Okay. PL by TE b1 minus b2 log b1 by b2. This is the final expression for the elongation of tapering bar with rectangular cross section. Okay. So this we conclude today's session. Thank you. Let us discuss some more examples in the next session.
Like, share and subscribe. Hit the bell icon for more updates.